All right, so next we have in the agenda is to demonstrate you some like projects that we have done in University of Moratuwa using ROS. Okay, so we have been using ROS for some time in projects at our department, Electronic and Telecommunication, and we are going to explain some of these projects so that you will also feel the motivation to use ROS in your future project. So when you see this, this will be an inspiration and motivation to start your own project. You will feel that, okay, I can do this as well, right? So if I move on. So I hope I have the access. All right, okay. So the first project I'm going to explain is done in 2016 when I joined the department and University of Moratuwa as a lecturer. In fact, this is my first final year project supervision. So it was an industry collaborated project with the company called Zone 24/7 to build a robot that can do inventory management for large retail stores. So this company have been working with one of the USA's large clothing shops, right? We are talking about really like massive shops, not even very like 10, 20 times bigger than a Kiel supermarket, right? Very huge stores that are there in US. So you want to do inventory management. So you want to find out what clothing is finished. So you have to fill that particular rack and so on. And we have very limited time because maybe the shop closes at 10 p.m. and it will open up again in 8 a.m. in next day. Right? So we have very small gap and it's a long area to cover. So this company has been working on developing a robot that can autonomously go here and there in the robots in the store and build a map and actually see what sections that need to be filled, right? So as a prototype, we did this project. So this is the robot platform that was created, and we use many like ROS tools for this. And here you can see you build a 2D map of the environment, and then along with that we have this 3D depth sensor, so you can build a 3D map. So from the 3D map now you can actually see where we need the supply. Okay, so if I go to the next slide. Right, so I'm not going to describe all these details, but one thing to note here is that here you can have these processes like grid mapping, navigation, autonomous exploration, 3D mapping. So all these can be converted to ROS, and here you can see a ROS-based PC, Intel i5 Ubuntu, as the main computer that we used for the robot, and we had a LiDAR sensor. You will learn about it later as well. It's like a laser scan, right? And cameras and many stuff. So I think best is to show you this video. Yes. So we had very limited space. Of course, we cannot be doing it in a large because this is just a prototype. So once we put the robot, we are not telling where to go. So it goes for the unvisited areas and build the map like this. So this is the ROS RVIS tool, right? So along with the 2D map, it also generates the 3D map. But in ROS, that is not there. So it had to be done as another thing in that. So you can manually do this. So here you can see it has obstacle avoidance. It does not hit with the obstacles or people there, right? And yeah, so there are certain aspects like loop closing. I don't want you to actually understand them. So in SLAM, there are certain things that we have to address. So that was the first project that we actually did from building the robot as well. And in the second project, I'm going to explain. Yeah, so this is the second project is the personal mobility system, right? So I think you have seen these kind of mobility systems like Segway produces these kind of things. So we wanted to build one at our university as well. And again, we use ROS to implement all these stuff, right? So we have the main, so we had actually a Raspberry Pi 3, right? Having the ROS navigation stack running. So here you don't have a lot of space to have a computer and so on. So we have all these processors nicely implemented through ROS. And since time is running out, I'll show you the video. So yeah, so there was autonomous navigation mode. So the human is just sitting standing there, and when we give where we want to give, we are going to go, it will just show, move the personal mobility system, right? So the map is being created. And also you can, using a joystick kind of thing, or from a phone, you can also manually navigate as well. So this is there. Then autonomous mode. Here, let's say we want to summon, so we park this vehicle somewhere and we want to get it back when we want to ride it. So it can autonomously go and avoid obstacles as well, right? Yeah, so, okay, so with that, I will invite Oshada to explain some more projects that we have done. Over to you, Oshada.
Thank you, Dr. Pesala. So I'll be talking about a couple of more projects done at UM using ROS. So the first project is actually my internship project. So my internship happened at CSRO in Brisbane, Australia. So CSRO has these cool six-legged robotics platforms, which they call as cyropods. So you can see there are different versions of cyropods. Like they have different arms and different kind of motors, different cameras, different sensors and all. So the interesting thing about these robotic platforms is they all run ROS, and all of these head supports are controlled by a single high-level controller called as the cyropod high-level controller. So it's actually a ROS based package. So I myself had the chance to work with two cyropods. So on the left hand side, you can see the Phantom Edge cyropod. So it's actually controlled by a Raspberry Pi. So I implemented this cyropod high level controller on the Raspberry Pi and control this robot. So in these above robotic platforms, they have sophisticated processors like Intel NUCs and all. So the on the right hand side bottom corner, this is the Z gyropod. So with Z, my task was to upgrade its system from ROS Kinetic on Ubuntu 16.04 to ROS Melodic on Ubuntu 18.04. So moving on to the next slide. So this has some tools in ROS which helped me to complete my project. So this is the RVIS visualization tool. So a base model of robot can be visualized in this RVIS, and this is the gazebo simulation environment. So you can actually control the robot in simulation before trying it out in the actual robot, and it can be very helpful because these robotics have expensive motors and sensors. So if something bad happens, it would be a very costly damage. So to prevent that, we can first run the simulation on gazebo and then move on to the real hardware. So this is ROS package written by myself. So it's called RQT reconfigure control. So normally these cyropods are controlled by a joystick. So I wrote this ROS package to control the gyropod using a PC GUI, graphical user interface. So this is part of the RQT graph. So it's a very large RQT graph. This robot has because they have many dynamical motors, right, like 18. And this is the RQT plot. So you can easily visualize the velocity commands and other data published on different topics, which would be very helpful to debug. So this LED robotics is a very popular popular area. So many people even now including people including CSRO are researching on this area. So because in rough terrains, leg robots can move better than wheeled robots. So moving on to the next project, we have some final year projects going on in this year on a self-driving car. So in this project, it's called the precise vehicle localization for self-driving. Localization plays a very important role in self-driving because it should know its location accurately, so that it can plan its maneuver. So it uses many different sensors like GPS, LiDAR, camera, IMU, odometer, and stuff. So those sensor data are then integrated through sensor fusion, and then it's used by different algorithms to estimate its location. And in the RS environment, you can actually visualize the output of the localization. So if you can see, there's a purple line and a green line. So the purple line is the ground truth, and the green line is the localization output by the algorithm. The bottom corner image is the LiDAR odometer visualization. So it's like the routes are there, and the output of the LiDAR point cloud is visualized in this image. Uh, so this is the RQT graph. So you can see it's somewhat complex. So it has different nodes like for IMU, GNNS, the visual odometry, uh, and stuff. So this stands for different sensors, and they use cameras as well. So for cameras they have sensors, and they have some processing nodes, and some evaluating nodes, and visualization nodes using RE. So the feeder is a data set actually, because current right now they are using data coming from a data set other than the actual sensors. So the next project is also a part of the self-driving car project. So in their project, they do dynamic object detection, tracking, and trajectory prediction. So in a self-driving environment, dynamic objects are very common, like passengers, cars, and other vehicles. So they try to detect these objects, as well as try to track them with time, to observe their movement, how it's varying with time, as well as predict. So what will they do in the next frame? So this is also a ROS-based project. So they use data coming from a camera, as well as the point cloud data coming from the LiDAR to do this task. So in the left side image, you can see when the car drives through the lane, the point cloud mapping obtained by the LiDAR visualized on RVIS. And on the right hand side, you can see how it's detect those objects like cars, passengers, and other vehicles using 3D bounding boxes. So from this slide, Bhanuka will explain about those projects.
Thank you, Oshad. So, yeah, following, I'm going to describe about 3 projects that are done in collaboration with the University of Moratuwa and CSIRO in Australia. So one thing, if you are like doing a good research project even in Sri Lanka, there's a chance you can collaborate it with other world leading researchers if you are using ROS environment. So this project is a legged robotic project, and it is done with the primary objective in hand, that is to assist human operators in a disaster response scenario. So the legged robots are very useful rather than wheeled robots because they can navigate in very unstructured environments. And here in this robot, you can see that there are 6 legs, and for each joint there is a actuator control in there. And here you can see that there's a sensor called Kinect connected here that can visualize the immediate terrain of the robot and identify the obstacles. And also this is called a 3D LiDAR sensor. So basically what it does is it takes a 3D environment around the robot so that the navigators can look in 3D where the robot is going, or create a map so that map can be used later to evaluate the disaster analysis and so on and so on. So this entire project is done using robot operating system, and the gazebo simulations have been used to validate the design. So this is a project done by one of my a group of my colleagues in 2019, and it is a quadruped robot. So that means there are 4 legs, and it is a bit strange design. As you can see, there are no actuators in these knee joints. So there are 2 motors. If you can see my cursor, there are 2 motors controlling this entire leg from this position, in the base position. And it can do some really cool complex movements of this leg tip. And so this is some a sort of a research project to identify the capabilities of this robot. So this is entirely done in ROS and gazebo environments. So because it is a new design and unconventional design, before they were designing the actual robot, so they did some intensive simulations to verify everything in gazebo environment. So you can see that they have verified everything, and after that they went to the building process. And in their project they included opening and closing foot to this robot, so that they can analyze how the foot is supporting when the robot is traveling in muddy environments. So you can see they have gathered data in ROS environments, and they have done a good research on that. And this final project is done by myself and 3 other members with supervision of Dr. Peshal, and also from CSIRO Australia. And this is a leg wheel hybrid robot. So uh, wheel robots are better for energy efficiency, and we know that because most of the people use wheeled locomotion like cars to navigate in very efficient manner, but they are not good for rough terrain. So if you have limbs or legs, you can navigate in very unstructured terrain using like patterns like crawling. So you can see how the robot is our design is navigating navigating our obstacle using the legs and wheels. So we have 3 wheels and 2 legs there, and we have a camera to see the immediate surroundings. So I will not go too much details, but I will tell you how ROS helped us immensely in this project. So one important thing is we need to identify the immediate terrain of our robot. So here we have a camera, and this is what we see from camera, and we can easily interface this camera using the manufacturer's ROS libraries. And we need to create the map of the immediate terrain like this, how the boxes are shown in 3D using REST environment. And because we didn't have much more computational power in this robot, we had a Raspberry Pi here. So we transmitted all the information from camera to a computer easily using ROS. We don't need any other libraries or anything. And we did all the processing in the laptop, and we give the commands to the robot again through this Wi-Fi camera. And also we can see how the robot is behaving using this ROS visualization tool. And even if we can't see the robot in person, we can see from this camera image and this visualization how the robot is behaving. So so those are some cool projects from that are described by Dr. Veshala, Oshad, and me about what we had done in University of Mortu. And Kitmin will tell about some good projects that are done outside Sri Lankan context, so you can have a better idea.
Thank you, Bhanuka. I believe I'm audible. Let me just get. Okay, I think I have control. So I hope everyone's having a great session today. So we wanted to introduce guys to the projects, the ROS projects that we have done at University of Moratuwa, but we didn't want to leave out what ROS can do in the global scope as well. So we've introduced some global projects, both in industry and research, that are currently using this amazing platform for its robotics applications. So our first project is this UGV called Jackal. It was developed by Clear Path Robotics. So as you can see, enjoy the video. It has a lot of amazing features. It's a small, fast, and entry-level field robotics research platform with a lot of sensors, very useful sensors that you can see here listed below. So they have a LiDAR, GPS module, and a stereo camera. It has also an onboard computer that is doing all the processing real time, and it has a lot of supported ROS libraries. And you can see there's a nice gazebo simulation. So this is, I believe, an excellent platform for robotics research and these kinds of terrain-based robotic uh, applications. Right, let's move on to the next one. So this is sort of a very handy robot, a robotic platform mounted with a single arm, robotic arm, and I believe it's very useful in these shopping environments, inventory management environments. So it's another robot from Fetch Robotics and can be used in warehouse for automated pick and placing tasks. So you can see here the robot is going to move towards the shelf, and it's going to use that robot arm. Yeah, we'll soon see that can do some pick and place tasks. So this is also supportive of ROS extensively, and it is equipped with some sensors such as this range finding sensor, an inertial measurement unit, IMU, and this prime sense short range RGBD sensor. So that's it can detect red, green, blue colors and also the mixes of those colors at a short range. So let's move on to our next robot, and this is a very interesting project, very exciting and extremely advanced project as well. It's a bipedal humanoid, and it's called Atlas, and it was developed by the Hong Kong University for the DARPA Robotics Challenge. So it's almost as high as a in height. It's almost as similar to a human, and it's much heavier than an average human as well. And it's also based on, as you can see, these videos, these nice videos showing all those different the perception, the walking simulations of Atlas, and there are so many other applications. You guys have been shared the videos in the chat, and you guys can watch these videos and learn about Atlas further.
The Apex is proud to announce the release of its educational.
So this is the Gapter drone. It's short for Guytech Copter, and it is a product by Guytech International, and it has the ability to fly indoors, outdoor, and can be monitored using the internet. So this is a very exciting project. It's a drone-based project that uses ROS. There's ROS support for this project, and it's equipped with Pixhawk, Odroid, and laser scan. And it also has 4G internet connectivity. So that's a very amazing another application that is a drone that supports ROS. So we'll watch the video a bit more. Right, so let's move on to the last two projects. So ROS in space. Now this is very exciting. NASA has, in 2014, NASA introduced this Robonaut, which is a dexterous humanoid robot built and designed at the NASA Johnston Space Center in Houston, Texas. And this robot can take over simple, repetitive, or especially dangerous tasks on places such as the International Space Station. So that's really cool for a robot to be able to perform in space, and more, as Dr. Faisal mentioned, what better endorsement than providing the confirmation that NASA also uses ROS on its space robots. So you can see that the robot is performing different kinds of tasks, and we hope that we can see this one day as a real space robot. And the last one, this is a very interesting video as well. ROS has gone underground. So this is a subterranean challenge, and you can see how they are using ROS in this challenge to control the robots and do the tasks. Right, so these videos links are available in the chat. You guys can check these videos on your computer as well later. Yeah, it's pretty cool what ROS can achieve, and all these different applications are out there: drones, humanoids, subterranean robots, UGVs, copters, and all sorts of projects have been developed using ROS. So I think since it's 10:40 now, we can take a 10-minute break, and you guys can relax, and let's meet at 10:50 a.m. again, and we can move ahead with the third session. That is, we can start with robot theory, and we can get into learning robotics with ROS. Thank you all, and we'll meet again at 10:15. You don't have to leave the meeting. You can stay here, and we'll meet back at 10:50. Thank you.